Okay guys, we are going to be looking at our 1.2 notes, our functions. Take these notes on your guided notes. If you don't have the guided notes page yet, that's fine. Take them on your notebook paper and you can copy them over later. That is not a big deal. Throughout the video, I will periodically ask for you to pause and try the examples on your own. Make sure you are doing that so you get a chance to try them, and then I can go over them. The first thing we're going to talk about is just a relation. So for a relation, think of a relationship between two things or two variables. For example, something like between doing your homework and getting a good grade on the test. That would be, there's probably a relationship there. Some of us experienced that on the most recent test. The homework does impact how well you learn and how much practice you get, especially in a math class, as a side note. Relations may be represented in many ways, such as verbally, numerically, graphically, or algebraically. Function is an actual specific type of relation. It's when each x value is paired with exactly one y value. So functions are important because they can be used for prediction purposes. So you might look at an ordered pair, and in order to determine if they are functions, you want to see if no two pairs have the same first element. Or what we typically would say, if any x's repeat, then it is not a function. So you're making sure no x's repeat. You can determine if the graph of a relation is a function by conducting the vertical line test. So that's where at no point through the graph could you draw a vertical line through the graph and have it touch it more than once. So anywhere on there, not like, oh, just this one point, it only touches it once. If any point on the graph, it touches the graph more than one time, it does not pass the vertical line test, and it is not a function. So I have some examples here. I want you to pause this, take a minute, and try to determine if each of these are a function. Okay, as a quick verbal check, if you have not yet paused, hit pause so that you don't miss this. Try it and come back. On the first one, looking at my ordered pairs, my x values are -3, 4, and 2, so none of my x's repeat, so yes, it is a function. On the second one, I have my x values of 4, 4, and 9. So since the 4's showed up twice, it either gave me a -2 or a 2. That is not a function. On the third one, my x values are 4, -3, and 3, so none of the x values repeat, so it is a function. It does not matter that the y values repeated. It matters whether the x values do. The fourth one is y equals x squared, which you should have a pretty solid picture in your head of a parabola that none of my x values repeat. It passes the vertical line test. Every x that I plug in will only give me one answer, so that one is yes. On the fifth one, that is a line. If you need to graph it in your calculator to get a picture of it, that's fine, but you should have a y-intercept of 3. It should go down 2 and right 1. That also passes the vertical line test. Every x only gives me one answer. The sixth one, I don't know that's actually on your paper, but just real quick, that should be a circle, right? Like it is x squared plus y squared, so it has a center at 0, 0, and a radius of 6. A circle would not pass the vertical line test. So that is just going to be no, not a function. On the right, my two graphs, the first one, no matter where on there I drew a vertical line, it would not hit the graph more than one time, so yes, it's a function. Whereas on this bottom one, if I drew a vertical line anywhere in these middle parts, it would hit the graph 1, 2, 3 times, so that one is not a function. If I'm going too fast at any point, feel free to pause it and take better notes. That's not a big deal. Next, we're talking about domain and range. And also, I'm going to go through a lot of this kind of quickly because this is all stuff we saw in Algebra 2. I just want to highlight it. So remember, domain is your x values or your input or your independent variable, whereas your range is your y values, your output, or the dependent variable. So we tend to consider the domain and range because it gives us an idea of what x values will actually work in the function and what y values are possible. So if I'm trying to graph it, I need kind of an idea of where it's going to show up so I can make sure that my window is set to accommodate that. On the first one, looking at my domain and my range on A, I'm going to do this one with you. So your domain is your x values. So my x values here are -3, 4, and 2. You can see where I've listed them out with the fancy brackets. It's a set of these numbers, just the -3, 2, and 4. Those are the only ones that were in my domain. My range was -6, -2, and 0, because those are my y values. Now, whether you list them in the order that they show up, -3, 4, 2 for the domain, or if you put them in order from least to greatest, that does not matter. You just have to make sure you have them all. I tend to list them in order from least to greatest, but would not count off in any way if you listed them in the order they showed up. Pause for a second and go ahead and try to do B, C, and D. On B, your domain is simply 4 and 9. Your range is -3, -2, and 2. So while B is not a function, it still has a domain. So, because remember, the domain and the range are the x or y values respectively in the relationship. It does not have to be a function. On C, your domain is going to be the -3, 3, and 4, and your range is just 1 and 2. So again, because the 2 showed up, you don't need to list it twice, you just list it the one time. D is your parabola. I can plug any number into that x squared, but all of my answers are going to be positive or greater than or equal to 0. So my domain is -infinity to infinity, whereas my range goes from 0 to infinity. Note that it's a bracket on the 0, because if I did 0 squared, I do get 0. And I'm going all the way up to infinity. There are two main rules we look at when we're dealing with domain. These rules will show up all year. So the first one is the fraction rule. That's what we call it, but you have for a long time known that you cannot have 0 in your denominator. Like, you cannot divide by 0. So whether you want to write out the words that I've written out here or just write denominator cannot equal 0, like an equal sign with a slash through it, that's fine. For your square root rule, we can't take the square root of a negative. It gives us an imaginary number, which is not real. Therefore, it messes up my domain. I do not get a real answer there. So for my square root, whatever's inside that radical has to be greater than or equal to 0. So any x value that makes one of these not true, so if it gives me a 0 in the denominator, or it gives me a negative inside my square root, is not part of my domain. Some examples with this, again, pause as needed. The first one, g of x equals 3 over x plus 5. So this is going to be my fraction rule, so I'm looking at a fraction. I know that my denominator cannot equal 0, so I'm going to just write an equation that says x plus 5 cannot equal 0. When I solve that, I would get that x cannot equal -5. So all real numbers that are not equal to -5, you're welcome to write it that first way right there. Or you could write it in interval notation, -infinity to -5 and -5 to infinity. So that literally goes from -infinity to +infinity, but just skips over the -5. That's why -5 is included in both of them, but with parentheses. So it goes all the way to it and then hops right over it. On the second one, we're looking at our square root rule, because I'm looking at a square root. Whatever's inside my square root has to be greater than or equal to 0, or cannot be negative. So I'm going to say x plus 3 is greater than or equal to 0. And that's what I'm going to solve. So I'd subtract my 3 over. I'm going to get that x is greater than or equal to -3. So that would be all real numbers greater than or equal to -3, or again with interval notation, -3 to infinity. On number 3, that uses both rules. Go ahead and pause and try that. So I'm just going to do the square root rule first because it shows up on top, and that's how I read top to bottom. It does not matter which one you do first. But I know that the inside can't be negative, so x has to be greater than or equal to 0. There's nothing really to solve there. That's going to be part of my answer. For the denominator rule, I know that, or my fraction rule, I know that that denominator cannot be equal to 0. So I'm going to have x minus 5 cannot equal 0. So solving that, I add my 5 over. X cannot be 5. So I end up with all real numbers greater than or equal to 0, but not equal to 5. Because if I say greater than or equal to 0, that's starting at 0 with the bracket and going all the way to infinity. But it also says I cannot be 5, so I have to include the 5 with the parentheses. Like, he's got to hop over that. Next, we're looking at our function notation. This should not be new. It's f of x, or f with the x in parentheses, but it's pronounced f of x. It means that f is a function of x. So as your x is changing, your x value, the f, the output, is changing. For these four, I want you to plug them in and solve them. And pause for a couple minutes and do those real quick. You're welcome to use a calculator if it's numerical. On A, plugging in -4, make sure you use parentheses, but as a check, you should have gotten -296. Plugged it in for each of these x's. On B, you're plugging the b in, so you just get b squared minus 6b. You can't simplify it any more than that. On C, you're plugging the c minus 3 in, so you will have to do c minus 3 squared, which remember is not c squared plus 9, it's c minus 3 times c minus 3. And then you'll have to do minus 6 times, and again you have the c minus 3 there, so you had to FOIL and distribute on this one. As a check, your final answer should be c squared minus 12c plus 27. D is actually, this is a piecewise function, so you're going to do f of -1 first, and it says that's my x value, so that would fall into where -1 is less than 0, so I'm going to use this top function. -1 squared is 1, plus 1 is 2, so f of -1 is 2. F of 4, that actually falls into a number that's greater than or equal to 0, so I'm going to use my 4 right here. 4 minus 1 is 3, so f of 4 is 3. Again, pause as you need to, make notes as you need to on things you want to ask questions on when you get in class. That's what we'll do the next day. Next, we're looking at our types of continuity. So the first would be continuous, and that's where there's like no holes or anything in the graph. No asymptotes, any of those things. We have removable discontinuity, which a lot of the times I will call point discontinuity, because it's literally just like this one point where, like, if I could just plug that point in, then he would be continuous. I could have a whole bunch of them, but it's just like a little hole in my graph. Whether it's this first option where the point is just moved up, or it's the second option where there's just a hole and there's nothing to fill it in, that still counts as removable discontinuity. Those happens if you have a certain value in your denominator that does not work, like one of the previous examples where it was like everything but -5. Well, at -5 you might have a hole. We'll talk about that later. Or piecewise functions. The next is jump discontinuity. So if you kind of look at it like, hey, I'm going along, I'm following this graph, this is great. Whoop, I jumped up here and now I'm following this graph. So there's a gap in my graph caused by the jump. Those happens for piecewise functions. We will get more practice with piecewise functions. I think it's one day next week. It's in section 1.3. And then the last type of discontinuity is your infinite discontinuity. This is when you have an asymptote. It's like I'm following along, my graph is going fine, and then, oh my God, it's going down forever and ever and ever. It's approaching a negative infinity or maybe a positive infinity. That's why it's called infinite discontinuity. That is a asymptote. And that's when you have a value in your denominator. So sometimes it causes an asymptote. Sometimes over here it might cause a hole. And we'll look at the differences in those a little bit this chapter, but a little bit more next chapter. The next thing I want to look at is your increasing and decreasing functions. So increasing and decreasing is really just as you're looking at your function going from left to right. So looking at this first one, I'm coming from left to right. My graph is going down. Oh, it's decreasing. The x values at which it's decreasing are, well, forever ago, wherever it started, negative infinity. -2 is the x value where it stopped decreasing. Then from -2 to 2, like it's neither increasing or decreasing. So we would call that constant, and that's between -2 and 2. And you can see again, you are using your interval notation for these. And then from 2 on to infinity, it is increasing. So I get to call that one increasing. I'm going to have to stop the video in a second because I'm hitting my max amount of time. We have a little bit more that I want to go through with you. I'm going to go ahead and put up the answers for the next two examples, but make sure you pause and see if you can do them on your own. And then I will pick up with boundedness on the next video.